Well, I will never forget the first time I organized an event like this one. The GR Roundtable in the Astronomy Summer School was a unique moment for me as one of the organizers. You should have seen how happy I was after I saw everything went as planned. I'm sure this time will be a fantastic moment for us all again. Today, we'll meet Professor Djuna Croon, who is a researcher in theoretical particle physics, astroparticle physics, and cosmology. Her work focuses on various phenomena like boson stars, Higgs sector, dark matter, and supernova explosions. She currently is an assistant professor at the Institute for Particle Physics Phenomenology at Durham University. Naoko Neilson will also be joining us today. Her research is centered in high-energy neutrinos, astroparticle physics, and particle physics. She works at the IceCube South Pole Neutrino Observatory on the BL3, a new neutron lifetime experiment using the beam method, and P1, the Pacific Ocean Neutrino Observatory. She currently is an assistant professor at Drexel University. Another participant will be Norma Graciela Sanchez. Her research is on the physics of the universe, covering physical theory and quantum physics from the early universe. Black holes, dark matter, dark energy, and galaxies and their structure formation. She currently works on the unification of quantum theory with the theory of general relativity, and the cosmological constant, and black holes of all types and masses. She is research director at the Centre National de la Recherche Scientifique and founder and director of the International School of Astrophysics, Daniel Chalonge and Héctor de Vega. Silvia Penati is also in today's panel as a string theorist. Her studies focus on high-energy physics and supersymmetry. She was chair at the COAST Action, which intended to create an European research network to study the impacts of string theory in other areas of physics. She is a full professor at the Department of Physics of the Università degli Studi di Milano-Bicocca. Katy Clough will also be joining us. She is one of the key authors of the software GR Combo. Her research focuses on numerical solutions to Einstein's theory of general relativity and its cosmological and astrophysical contexts. She is a Science and Technology Facilities Council Ernest Rutherford Research Fellow at the Queen Mary University of London. Finally, Patrícia Gonçalves will moderate this roundtable. She is the coordinator of the Laboratory of Instrumentation and Experimental Particle Physics projects related to space in the area of space radiation environments and effects. The main focus of her research is astroparticle physics and the study of space radiation environment. She is an associate professor at Instituto Superior Técnico. This panel will be discussing two topics of major importance nowadays. The first one will be women in physics. In a world where gender equality is estimated to be only achieved in 135 years, and having physics one of the biggest gender gaps in STEM, discussing this topic, its possible solutions and causes, it's an essential step forward. The other topic, astroparticle physics, is a very recent area of research with exciting new physics to explore. Most people are already familiar with astrophysics, cosmology, gravitation, and particle physics. Astroparticle physics, however, is a relatively recent branch of physics. In this part of the roundtable, it will be discussed how astroparticle physics tackles the big questions in the above-mentioned areas, and the different lines of research that it pursues nowadays. Finally, before we start, I would like to thank everyone present, our audience for their interest, the team that helped me organizing this event for their support, the panel members for accepting our invitation, and Professor Patrícia Gonçalves for moderating this roundtable and giving us useful advice about its preparation. Well, I think we're ready to start. I shall give the floor to you, Patrícia.
Hello, good afternoon to everybody, those who are in the panel, the Astron Feast students who have organized this discussion, and also people who are listening. I hope you're going to enjoy and learn and also have food for thought from our discussion. So I have some first part of our conversation will be about women in physics, and there are some questions and themes that I'd like to cover, and that I think they will be useful and interesting for us all. So thinking about physics, okay, physics doesn't have a gender, it's a science, yeah? So why, so science is is something that humanity has developed. So why women in physics? Why is it so important to have women in physics, and why are we worried about this? Can any one of you start to answer? Maybe provocative, I know, but can you start? I don't know.
I don't know if you want, I can start.
Yeah,
I don't know if you have an idea of that, how to organize the discussion, or we can just propose ourselves. Okay, just talk. Yes. Okay, thank you very much. Well, first of all, good afternoon, everybody, and thank you very much for the invitation. This is going to be a very great event, I think. And, well, in particular, because it focuses on two great problems, a scientific problem and a gender/scientific problem. Okay, so we perfectly know, as you said already, that we have a severe gender gap in physics, in particular. Well, I'm a theoretical physicist, but more or less I think we are theoretical physicists, and in theory, the gender gap is even more severe. So, well, beyond asking ourselves why, and maybe we can discuss later why, the point is why we should worry about that. Well, once we know that there are, of course, many reasons which can go from educational, cultural reasons, unconscious bias, conscious bias, whatever you like. So there is a problem created by some obstacle which prevents women, or discourage, not really prevents, but at least discourage women entering physics. Then we should ask, well, why we should remove these obstacles. And I think the answer is, well, beyond the fact that it is, of course, a sign of civilization. I mean, this is socially correct, to allow everybody to do whatever they like or whatever they think to be suited for. Just we should guarantee the freedom everybody to choose what they like to do in their life. But beyond that, I think there is also a strong interest from science itself to be extremely inclusive and not discriminating, because of course it is an obvious thing, a very simple statement that I can make, which is the following: if we somehow even unconsciously discriminate or discourage part of the humanity doing something or entering science, we immediately risk to lose talent, to cut out from the very beginning potential talent. I mean, people that potentially could bring new ideas and new progress in science. And this is, of course, not in the line with what science should do. So that's why I think it's obvious that we should try to counteract any obstacle which prevents women to proceed in a career in science.
Can I follow up on that, Patricia?
Yes, please.
So yeah, I think that's a great point. So I think there's this point about, science is poorer when everyone doesn't participate. But I also think it's also important to stress the benefits to women of being in physics. So physics benefits from women participating, but I think women benefit from participating in physics. We talked a little bit before the session started about cultural differences, and certainly in the UK, physics is seen as a prestigious career. Being a theoretical physicist, puts you up there, people listen to you, you can have opinions on things. Even if you don't perhaps stay in academia, studying physics takes you into pathways in tech, in banking, in these kind of, positions that give you a seat at the table where decisions are made. And I think it's really important that women get a seat at that table, and that women are, involved in these kind of big discussions about moving forward in all aspects of society. So yeah, I think, as I say, physics benefits from women participating, but I think women also benefit from that participation too.
That is very, very interesting, this way of looking at it. And it's really, I think I never put it that way. And this is, well, not never, but it's not the more frequent way to put it. And I think it is very important.
Yeah, I think sometimes, we're telling women, oh, well, physics needs you.
Yeah.
But, we need to also be telling them there's something in it for you as well. There's some reason why you should actually want to do it. And, you could enjoy doing it. So it's got a benefit for you as well as just being something you're doing for society.
Yeah. But does anybody else want to comment on this aspect?
Well, I think these are both excellent points, actually. I just wanted to sort of say Silvia's first point was kind of about, often you ask the question, like, why does physics need women? But, why is it important to bring women into the fold? But actually, I think it's really about removing obstacles that are there, because women are already there. Girls and women are interested in physics. It is really about preventing them to be pushed out of the field, really. And why that's important, I think that's just, I think that speaks for itself. Like, we should prevent people to be pushed out of careers that they would like to do.
Okay, you mentioned people being pushed out. Can I just add something to add to your answer, Norma? Can you also focus on why do you think and how women can be or are being pushed out of physics?
Okay, yeah, I think in so many ways. I mean, there's a lot of research about this as well. Like, a lot of women in physics and gender minorities in physics experience sexism, greater or smaller acts, everyday sexism, but also, bigger issues. And I think beyond that, also kind of the sort of whole societal context about, like, how people perceive a career, like being sort of slightly pushed into different directions. I think that's plays a big part in who goes into what field at the end. So I think it's really about removing these barriers that exist, and then we can talk about, like, what a fair representation actually looks like.
Yeah, we'll get to that. I think Norma wanted to say something, and I interrupted because I wanted to get a bit more information from you, Djuna. Yeah.
I mean, taking into account what already have been said, I would like to point out that is why, I mean, to your question, why it's important to bring women to physics. Well, the question is more general, as Silvia already touched. I mean, for me, it's a question of a choice of society and a choice of some stage of civilization. I mean, humanity. And so it's not constrained to physics only. It could be put in more way, the women to the activities of society, all, I mean, influential activities. In physics in particular, it depends on the disciplines. There are disciplines and there are countries in which there is no so minority. And the same question could be also for a society, an inclusive society, and given the equal opportunities and equality and equal rights, equal rights, it could be posed also in terms of minorities and also in terms of countries and so on. So the problem is, in some sense, it has several aspects, which today it can be try to make some, at least partial, if not complete, synthesis, not including society, evolution, the question of minorities and the question of women, of course. And that depends of the continents, and that depends of the country inside the continents and the culture. The second point about physics, as I've said, depends also on the disciplines, and there are some one in which there are more and some one in which there are less. And about the point which was mentioned on the role or the prestige set depending on the disciplines, that depends that depends on many ways. And I don't think that the motivation that should be pushed ahead, forward, to attract women or whatever people good is interesting for science, and in particular physics, is the question of prestigious or the question of power, or the social position you can have in a bank, you can have in whatever, social position. If you really want to have power and social position, perhaps an economic, social economic, perhaps science, and in particular fundamental physics, is not the most say attractive one. Now science is attractive and passionate by itself, and irrespective of the boundary condition. And this is the power of knowledge, the power of the progress, and to go deeper and systematically in the most fascinating questions. And that you can do science fascinating even in the most hostile societies for women, and the most poor society to do fundamental science, in particular fundamental physics. So, in conclusion, it's to have women, one of the minorities which are women in physics, is attractive and is important by itself, and it's to people who are in a position to make opportunities and attraction, to convince all whatever, the different levels, and even the students and so on, the students who are motivated, you cannot, and to set, pave the way to reach and give the opportunities to them to develop their possibilities. So I wanted to make this point. Thank you.
Thank you, Norma. I think I will just put some more question in the table, and then I give the word to Naoko. But we have been discussing this now, but we are all aware that depending on the field of physics, as Norma has mentioned, there are more women or less, but there is actually, in all of them, there is a gender gap. I think there's no field of physics where we have no gender gap. In all of them, we have, some are larger, some are smaller. In theory, I think it's typically larger than an experimental, but I'm not sure. It also may depend on the countries. But Naoko, yes. What's your take on this?
Yeah. No, that depends.
Yes.
That depends even of the sub-disciplines and the interior. For instance, in theoretical physics, that is evaluated in the last year. In experiments, in astronomy, there are many women in astronomy.
Yes, exactly.
And that depends also on the country, but you have and there are developing set, or more peripheral countries, in which women and which science is not so well represented, but in the proportion are women who are best, who are doing the studies to go to the university and is a way to reach a position for them.
Yeah.
And so it's rather, of course, the general trend is there is a gap.
Yes,
And,
exactly. This is what I meant. The general
there is
trend
a
is
gap,
that there is
but
a gap.
It's interesting then, I mean, now, to do some more fine structure in terms of the countries, on the disciplines, on the continent. But I think
but I would like
there are programs in different
Yes.
continents, in particular in Europe and in the countries which are interested by this question, which analyze, I mean, people.
Yes, but in general, for our audience also to know, what do you think? And I would like also to hear Naoko. What do you think are the main causes of this gender gap? Do you think women are not interested in physics or in STEM? They are not motivated. Then when they get there, do they have difficulties? What happens to us when we have kids, for example? How is it? How can we have a career? Naoko.
Yeah, so far the discussion's been so interesting. Of course, women are interested, and of course they have what it takes to become a physicist, and of course they work hard and they're as talented as the men are, right? And just to throw back to the conversation previously, I thought the point about civilization was very interesting because, 100 or 200 years ago, most places you not only had to be a man, you had to be a very rich man or a nobleman to do physics. So nobody's advocating that was a good model. So why should we not further progress this, right? So I thought that was an interesting take. So yeah, why do we? It's hard. The gender gap is not only that there is an absolute gap, but as you get further along your career, or the people who are higher in rank tend to be more men. And so it's not just that there is overall gender gap that's different between countries and cultures and disciplines and subfields, but also I think in all of them, I think I can generalize here, the top are more men heavy than the bottom. And I think that creates a very difficult dynamic, because at some point in any field, I believe you need to be promoted up, if you will, right? If you want to go from being an undergraduate student to grad school, you need professors to write you good letters, right? If you're going to be hired as a postdoc, you need somebody who's hiring to believe that you are worthy of a postdoc. So at every stage, you need to be promoted by somebody. You need to be approved by somebody. And that approval most likely comes from men, right? So already there's this very bad power imbalance that we're up against, just in terms of pure gender ratios. And we're not even taking account like gender minorities. In the US, we have a racial problem, so that also plays an effect. So we're not even taking account in that just generalizing just women, right? Women have a hard time because we need to be approved by men at some point to progress in our career. And I think that is where things start to hard for us, because when somebody says, oh, who do you think is good, you tend to pick people that remind you of yourself. And if you're a very old white man who, and I don't want to generalize either, there are brilliant white men out there who are passionate about gender equality, but if you ask most people, does this person remind you of yourself? It needs to be somebody that looks and kind of sounds like you and comes from the same background and talks like you and acts like you. And that is a very hard unconscious bias that is hard to get rid of, I think. So I don't know what the other panelists thinks about this. So I'm going to return the floor because I'd like to.
That's interesting, because this also has to do with the way your work and your performance in your work is judged depending on your gender. And this is one of the issues I also wanted to address. So please feel free to comment and I don't know who wants to start.
Well, maybe I can add something. I support and I agree, I totally agree with Naoko and what she said about the reasons. I find that, well, of course, I'm saying something obvious, but I find that the worst set of reasons, worse in terms of trying to solve the problems, so that the worst set of problems is indeed related to, you know, unconscious bias and stereotypes, because we are all victims of cultural stereotypes, of course. And as I'm used to say, if you think of, you know, the prototype of a theoretical physicist, the genius is Einstein, of course, and everybody has Einstein as, you know, the light, what we want to tend to, but not for women, of course. A woman will never look like Einstein, and probably she doesn't want to look like Einstein, you know. So we are trying to bring inside the community of physicists even a different way of doing physics, of discussing physics. You know, many times being aggressive, being very assertive is considered as being very intelligent. This is not true. Of course, women in general are less assertive. They tend to say things when they are sure that what they are going to say is correct. And this is considered in the opposite way, you know, as sort of weakness or something which is not a plus when you have to judge the person. So, and this I find very, very difficult. This, of course, then affects any decision making inside commissions, inside selection commissions, committees. And this is something that I find very, very hard to counteract. So I would like even also to listen to some new and fresh suggestions on how we could fight against this, let's say, this unconscious bias that affects selections.
Yeah, that's interesting. Then we have Djuna and then Norma. Yeah, hands up. So Djuna.
I think Norma was first, actually.
So Norma, I didn't see them. So Norma was.
Thank you.
I'm sorry.
Yes, I agree with Silvia and its point. Now, I mean, this collects in some sense those two kinds of gaps or extreme bias. The one is that, I mean, placing as an example Einstein, in fact, is a question that the social and the society and the history and the fact that at the time women were not so said visible or so numerous respective. The fact is that not even against or versus women, the figure of Einstein today in the media, even in the academic, etc., in some disciplines, monopolize the framework because it's a question that it's a bias itself that also does not allow to see other figures as important or who have made a lot of progress and before and after, etc. So this influence of the culture, of the communication, and how to promote or natural. This is a point which hold for all. In all, and in particular in science, and takes for women, of course. Marie Curie, for instance, who can. If one to I said Marie Curie because she also was,
Yeah, 2 Nobel Prizes.
Singularity said. But this, the way in which committees work, the way in which science works, all that also have bias. And inside that, it appears that women, have then the difficulties to be promoted and so on. But I think that it's a question also of the way in which the way in which science, more general, the organization is the organization of science, of society works, that promotes because many factors, some of them are not understood yet. And then you have figures that are promoted or that are more in celebrity than others. And that is a bias. And the example of Marie Curie now, because of the fellowship Marie Curie, that is relatively recent, she has not been elected on the Academy of Science, for instance. And as others, we have examples, histories, people doing history of science can retrace and is retraced. So I think the question is more general, and the fact that we are discussing of women, which is important, the problem should be posed, but need to be also interrelated with all the other biases, which are generating, which is the background to generate more difficulties.
Yeah, thank you. Djuna, now it's you.
Yeah, I think they were all really, really good points. I just wanted to bring up this extra effect, which I think is also quite toxic, because what I find myself, or I hear sometimes, and I think more often than not, I would not be told these things. So perhaps it gets more spoken about than I even hear. Is whenever a woman or another minoritized person does succeed despite all these barriers, and for example does really well, gets great job offers or wins prizes, that people then start to assume that it is because they are a woman or a minoritized person, because obviously now there is some performative efforts going into diversity, and therefore people start to assume that actually perhaps it's easier to be a woman because there are diversity hires now, and therefore whenever someone does well, then people start to assume that it is because of some unfair advantage, and I think that's also kind of a toxic effect that we're dealing with now.
Yes, it's the backlash of the diversity hires, but this doesn't happen in all countries yet. We don't have diversity
in all countries.
Yet. We don't have. Yeah. So
in which countries does it not happen?
We don't have diversity hires. We are favor, in Portugal, we favor hiring women to reach a certain number of women in the institutions, but they're not. You don't have quotas.
No, I find that doesn't actually even matter whether or not it's realistic or not. People just need to think that it's the case. Yeah.
So Katy, no, it's Naoko. No, I have her here. In the hands up.
Oh, so yeah. I actually I want to come back to Djuna's point because I think that's interesting. But I had a short thing about a representation of physicists. So I have 3 kids, so I've been pregnant quite a bit, and I give a lot of outreach talks. And when I was pregnant, I would give outreach talks, and I would always joke, "Well, you've never met an astrophysicist before in your life. Now you've not only met one, you've met a pregnant one," and that would always go over well. So I just wanted to mention that. That's all I wanted to mention, but actually Djuna brought up a good point. So my take on the whole backlash of, oh, you're only here because you're a woman, or you're only here because you're not white. My answer to that is always, well, you had all the, privileges and not having obstacles as a man, and this is how far you got. Like, I've come to the point where I just don't care about that anymore. Like, I've come to the point where I can actually say, well, oh, you think I had a unfair advantage? Like, you had all the advantages in the world, and that's how far you got. So maybe there's something in me that's deserving of this. It's kind of like how I'm always like, I kind of got, because I've been told that my whole life, I kind of got over it recently. I'm like, yeah, I deserve this, because look how far you came with not much and all the advantages. Like, it's a very combative attitude, but I think it's okay to think that.
Do you think men are concerned about these gender equality measures that are being taken? And I have Katy there.
They are very concerned, very
Yeah,
concerned.
I wanted to know. Katy, your hand is up, so maybe we can continue.
Oh, yeah. So, well, I guess I just wanted to chime in on that. I was really pleased to hear Naoko saying that she didn't care anymore, because I actually also reached that phase recently.
Yeah.
And it was such a huge relief. Like, I just suddenly thought, I don't care what you think of me. I'm successful, and I've been successful for my own reasons. And I think, that can actually, coming back to this idea of barriers and obstacles, there's the external ones, but there's also the internal ones. Research is really tough, and a lot of the time you do something and it doesn't work. And, you can sometimes take that as a sort of, that's a sign from God that I'm not meant to be a physicist. I'm not Einstein. I haven't got that, I haven't got it innate in me to be a good physicist. And, that's such nonsense, there's no right way to be a physicist. And I think when you can get over that kind of idea and just say, okay, it didn't work for me this time, but I'm still going to keep going, and try and remember your successes rather than your failures, and, take your successes and not kind of apologize for them. But really, when someone says, oh, well done for getting this prize, you just say, thanks. Thanks. Instead of saying, oh, well, I didn't really deserve it, I'm not really good enough, sort of things like that. So I think it's really positive to hear other people saying, okay, maybe we don't have to care about this anymore. Maybe we're just going to not care what people think. It would be great if we could all kind of get to that stage.
But one thing I heard is that maybe it would be important, or it would have been important, to have role models in the beginning of our careers.
Yeah.
And this is something that was also focused by Norma, is that there was this, Einstein, the communication, the scientist. And it's not even a role model for also a lot of men. They don't have to be like Einstein. Yeah. Yes, and the problem is that, and then this is not good for people to follow the one role model, the one that is communicated in the broader, to the more broad audience. And maybe we should try to see if we can get with our communication departments, for example, to get more communication towards a positive role of women in science. And this is something I've been seeing in a lot of places lately, like in the social network, for example. But I don't know, Djuna, you still have your hand up, so maybe you want to comment.
Yeah, I mean, I think that's a great point. I just wanted to sort of quickly respond to Naoko and Katy. I mean, I think that's absolutely fantastic that you got over it. I think I'm personally over it most of the time. Like, I don't know if it's all of the time. But then, I just think, like, was it really fair that you had to go through this, process to get over it? And like, and you probably indeed like had what it takes. And personally, I think for me, what it took was a lot of, I'm really stubborn, but then it's like, is it really right that the stubborn women make it, or, the very courageous, like, the women that eventually grow over it, that they make it through? Because perhaps there are women there that are slightly less stubborn than myself that, would be fantastic physicists, but don't actually, manage to kind of, get through all of this, like, bias that they have against them. but yeah, I mean, also great points about role models. Yeah, I think that's a great further thread for the discussion.
Yeah, but I was also something I already mentioned is when you start having a family, some of us have kids here and at different ages.
And my kid is actually crying at the moment. That's why I'm a little bit distracted. But yes.
Yeah, that's normal. And did you feel a big difference then at this stage and to get back to work? Because normally we have kids at the stage of our lives in which we have finished our PhDs. Normally, sometimes it's not like that. And then we have to build the career, and then we have the kids in our 30s, and then it's terrible because it's at this stage where you feel, okay, and what about now? I have a kid, I need to, how do you do it? How do you think that we could cope better? What is your experience? Naoko, hands up.
Yeah, so this is very much my lived experience. So we had I was pregnant with my first kid when I went to faculty interviews. So for those of you who don't know, in the US at least, the normal progression is you become a graduate student, you become a postdoc, and then there's that crucial step from turning from a postdoc to a tenure track position, which is an assistant professor in the US. So this is your first, you're trying to become a first level professor, if you will. And this has the promise of becoming like a lifelong professorship. So this is a very crucial interview process. So the first year I was on the job market trying to become an assistant professor, I was pregnant. I was throwing up 24/7. And these interviews, at least in the US, are all day. They start at breakfast. You have a breakfast conversation with somebody, and then you do interview, lunch with interviewers, interview, talk, brief break, then dinner with. And at that point, I could not keep food down. And I wasn't showing yet. So I would act all pleasant at lunch, take a couple bites, talk about my research, and then quickly in the 5 minutes I had between that and the next interview, run to the bathroom, throw up, get myself back together, go back out again and talk about my research enthusiastically. And then so usually you do this a couple of years to get the job you want. The second year I did this, I was obviously a new mom. I had a newborn baby. So I was breastfeeding. So I was pumping. So I would ask the schools I go to interview for, can you please block out some time every couple hours because I need to express breast milk. And this is not a choice. If I don't do this, I'll get sick. You can't just stop extracting breast milk. I'm sorry, this is very biological, but it's important. You can't, it's not a choice. You can't turn on and off a body like that. So if you are continuously breastfeeding, you have to express the milk out. Otherwise it gets you get very sick, right? So I would ask this, and the people who are interviewing would see that I have a blocked out time and say, oh, it seems like you have another 20-minute blocked out. So let's just keep talking. And, so it was hard. And then, of course, we had a newborn, and actually in a lot of cases like ours, my husband is also a physicist, and we were on the job market at the same time. So we did a lot of baby handoffs at the airport for us to travel, because you have to travel for interviews. And in the US, it's a big country. So, you can be on a flight for 5 hours to go interview. And that was a very bad year for us, very bad year. So I think that's when I kind of broke and decided, you know what, this is not working for us. Like, I don't want the fancy job. I don't, maybe I wanted to be at an Ivy League or like an MIT professor, but you know what, that's not my goal in life anymore. I want to be with my family as well. I want to be a good physicist, and I want to be with my family. And there's different ways to be a good mom that doesn't involve, being with your kid a long time. But for me, at least for me, the way I wanted to mother was to stay with my kids most of the time. And so I had to make some hard decisions, and not just me, my husband too. We had to make some very hard family decisions that year. And of course that impacts your career, right? But I think, what am I trying to say? I have no regrets. I have no regrets of the choices I made that year.
Yeah. But do you think it was as difficult for you as for your husband, for example? I don't want to get personal, but the question has to do with women how we feel this part of this phase of our career, and if it's how is it for men? Do they?
That's a great point. I mean, obviously, the physical effects were all me from childbearing and nursing. So obviously, it was more difficult for me. I think if I did not have a supportive husband at that time, I would have quit physics. So that means it was hard for him too, because he was trying to make it work for me as well. If we were married and I was a stay-at-home wife, or even if I wasn't, even if he didn't care about my career as much, I think that would have been a different story. But I think the good thing about how physicists are like younger physicists are, especially the men younger than us, or me at least, are very aware of this, right? Are very aware of the differences and are very supportive, at least most of the times. And I find that to be very hopeful. Not just the women younger than us, but the men younger than us are very in tune with this. And my husband is a great role model for them. And I think that's where I have a lot of hope in how the field will progress.
Yeah, that's good. Yeah, Djuna, you still want to?
Oh yeah, sorry. Yeah, I mean, I think that's also hopeful. I just had my first 4 months ago, and I think like I was actually lucky that I did have a permanent job when I had him, and I say lucky, but actually this is something I thought about and try to plan as much as you can plan an academic career, which is not very much in many stages, like for maybe a decade, before it actually happens. Because it is very hard and still, like, even having job security and being pregnant, I was still wondering how one dresses, for example, at a conference with a pregnant belly, and I realized I'd actually never seen someone at a conference before that was pregnant, and then all of a sudden I was over being the only woman in the room, but now I was also pregnant, so it's this other layer of being different, so I think, it was a very interesting experience for me. And I was definitely kind of thrown back into my own kind of like, what's it called? Like imposter syndrome a bit again. And now, obviously, I've been on maternity leave for a little bit. So I don't have actually any experience yet with the returning to work after that. So I'm actually very curious to hear other people's experience with that, because I'm kind of, it's a little bit daunting for me to kind of step back to work and now have a baby as well,
I don't know if anybody wants to comment or add some point about this. I think that it's a crucial phase in our career. Normally that overlaps with the babies and all this, and it's important. And I think it's important that the institutions in which we work are supportive and are aware of this, and that the potential of women does not go away with maternity or family. On the contrary. So, but I don't know. I'm not supposed to be. I'm just supposed to be moderating. So I don't know if you have more comments on this from our. Yeah?
Well, yes, I definitely agree that we need some objective support, but in general, supporting families, because of course we have the problem as mothers, but also fathers young fathers may have problems, same kind of problems. First, so this is something which I find probably easier to solve. Just question of politics to implement. Politics towards helping young people and young families. But what I found in my case, that when I had children was a different age, probably it was even worse. But what I found mostly difficult was to come back working. Come back for me was really really hard, because I tried to spend very few months home, the minimum that you are forced to take, the minimum leave of absence that you are forced to take in Italy, which is 5 months. So I took just 5 months, but it was just enough. 5 months were just enough to lose completely any collaboration. I was kicked out from all the collaborations because my colleagues were really, in that case, I don't know what to say, not at least nasty. They, they just supposed that I would have taken care of my child, period. I would have never done physics in the future. So why we should keep working with her? They try to remove me from my office and give the office to somebody else. But as I said, it was a different age. I mean, now I'm happy that I think this, at least, sort of positive attitude, even from colleagues, more positive attitude from colleagues now is expected and is too. I mean, I don't think that people now think they can behave this such a way nowadays.
Probably. Yeah, I think this depends a lot on where you are in your country. There are still
that's
countries
true.
in
That's
which
true.
women are not even allowed in the street.
No, that's probably true. Yes, but probably
so
I hope to be will. I mean, I try to think, positively, that there is more sensibility, at least, toward these objective problems which have to do with, with reconciling the private life with professional life. This is for everybody, because this is an objective problem for everybody, indeed.
We should be finishing the time for this subject, but I have just 2 questions. One is from the audience, and one is some about quotas. So you think there should be a 50-50% imposed distribution at the workplace to start to women, men? Do you think there should be some or that there should be some interval, I don't know, between 30 to 50? How do you feel about this? And also taking into account this, something we mentioned before that has to do with the way women are treated. Say, okay, you're here because you're a woman. We know that there is this problem. So how do you feel about these quotas for women? Norma.
Well, thank you. I didn't thought to answer for this question, but in any case, I think that it's not by an imposition of a number 50-50 that the problem should be addressed. Is by, I mean, say in the countries, in the continents which are in which the question of women, even of minorities, are conscious that must be addressed and solved and so on. I think that is by the politics, the politics in the institution or a more general level, that this question must be addressed. You cannot impose, for instance, in some disciplines to say, we need 50-50. And well, I mean, it could work. It could work. It could be a way. But I don't think in the imposition. And most we see most in the list or in the committees or in the, there are some quotations set or percentage in which women, I mean, that guarantee that a diversity of women is represented. And that, I think, is a manifestation of the inclusion of the degree of set of understanding of society that most countries will say yes. Now the practical one thing are the the statements, the documents, the written document, then the practice well, if you talk to people, there are different, it's not homogeneous, but that is not only for physics. I mean, the fact that of the family for women who have children and so on, it's not only for physics, even not for science, as you said. But that correlates with your other question that you posed. I think is the question number 10, the last question of your questionnaire, which I think is important at the moment now of the societies, of at least in Europe. Are the workplaces designed to suit both genders? Because if you take into account that in the workplace or nearby, you should have a place in which women who are working in those institutes or nearby can leave the children when they go to the office or they want to work, and then after take away because the children are there, they are nearby, all that is organized as the way, I mean, the same way they are organized, they serve restaurants for people to take restaurant in the same place or the coffee and so on. That is I mean, it's a progress, are also help to the practical life of every day, because you have helped with that. You don't need, I mean, to organize. Of course, I mean, but that is life in some sense. You need to organize your life. I mean, that is. But this question, are the workplaces designed to suit both gender? It's not a question of the offices. I mean, no. It's a question of those kind of services.
Yes, it's the support from the institution.
Yes, because the problem was touched about the kids, about the children. I allow myself to pose this question, which is important. This question, which I know very many institutions who do that, organize their own kindergarten set, their own kindergarten, and it's for companies, it's for science institutions, and so on. There are other institutions. And that depends of the, I mean, that depends of the tradition, well, of the culture and the evolution. This is a good point to take into account, because it's some kind of the right, a progress in the right of women and or young fathers said also, because in some cases is the father who take the children and the place in which he works, because there are these kind of services. I think it's very interesting.
Yeah, thank you, Katy. And then I have a last just question from the audience, and then we have to move the subject. But Katy.
Yeah, I guess I just wanted to say I didn't actually know about the 50-50 thing. Like I have mixed feelings about it. But I wanted to say in relation to that, you know, what I think we should do is follow evidence. So I think we should try and, like, sometimes we have feelings about strategies where we think, I don't like this strategy. But for me, if there's evidence that it works, then we should follow that strategy. Like, you know, as scientists, we should follow the evidence. So I think there are actually a lot of interesting studies into what makes a difference in trying to improve the gender ratio. And we had an interesting talk by someone who was talking about, you know, how when they were shortlisting, they were kind of enforcing the same amount of time spent discussing each person so that women got as much discussion as the men got. And that they found that just doing that really increased the number of women that they shortlisted. So I think these kind of activities that are kind of proven to work, you know, whether we personally like them or not, we should do, you know, what is proven to work. And maybe that needs more research. I don't know. But yeah, we should follow the evidence as scientists.
Yeah. Thank you. So I had a last question that is a bit, so it's from the audience, it's like, I think that this is the question. I think that during difficult times like wars or a global pandemic, the topic of gender equality gains a lot of attention. as it happened during the World War II, when women started working in factories and other industries where men used to work. Yeah. So did this happen during COVID? And also in the Ukraine invasion, are these opportunities to reduce the gender gap? Well, it seems very multi-factor question, but okay, it's from our audience, so maybe you can comment on it. I don't know who wants to comment. And if you didn't understand the question, please let me know.
The only thing that I comment is that I know, because I read some articles about some statistics collected during the COVID period, that of course we can imagine that this is a situation. It was a situation, women, particularly women in academy, so I'm talking about physicists in particular, where women were much more affected by the COVID situation, let's say, compared to their men colleagues, because in particular young women and young families. Because the same thing is true for if you compare young fathers with older colleagues or colleagues without children, because of course we were all stuck home, and if you had to stay home taking care of your small children 24 hours per day, you couldn't work. So this affected, at least I know a lot of my colleagues, women, young women, but also young men that were affected a lot by the situation. And in fact, you can see objectively that they were affected from the fact that their scientific production went down.
Katy, yeah.
Yeah, I just wanted to say I agree with that. I think it's been a complete disaster for women, the pandemic. For the women I know, I think it's been extremely tough. I mean, I don't actually have children, but for every woman I know who's had children, she has become, the default carer, and her career has suffered, regardless. And so I feel really angry about that. And so I think the only positive thing that could come from it is that I think a lot of people were kind of shocked by, they felt, when their life was going normally, they felt like, okay, things are kind of equal and everything's okay. And then there was this huge thing happened, and, all of the burden fell, a lot of the burden fell on women disproportionately. And I think that's probably shocked a lot of people. And I hope that will lead to some reaction, these kind of big events can be a catalyst for change. So I hope that will happen. But I think the actual event itself has been a catastrophe for women.
That's quite, yes, it was a problem. And I think that one thing that we were saying before, that institutions, when they're working properly, they can really be a very good support and solution for this kind, for overcoming the gap. And that while during COVID, the institutions were stopped, and these problems came back again. So institutions can really help in the progress, not only us as individuals, but the way the institutions are organized. And I think this is a very important point from what we have been discussing in this the debate today. So of course, we could go on talking about this here for hours. But we have to move to science. I don't know if you have any final remark about this, but let's. If not, I will move to the science part, to astroparticle physics. So from your curriculum, most of you work in theory in astroparticle physics, yes? Yeah. So my experience is from the experimental side. So this is going to be really interesting. So who can tell us what is astroparticle physics? It's a name that puts together two different things. Like 20 years ago, you were not talking about astroparticle physics like we do today. Who wants to start? Norma.
Thank you. I think that is not so true that 20 is the evolution of physics and of particle physics and of cosmology, that and the evolution of knowledge, of course, that make the emergence of new correlation, and you need intercorrelate. You cannot. I mean, if you think in the evolution of particle physics from the beginning of quantum mechanics, you see the evolution of the new disciplines and so on. astroparticle physics is not so new. It have more, more than 40 years. And in the last century, cosmic rays were the astroparticle physics at that time. The point is that the word astroparticle physics was coined relatively recently, said more than 30 years ago for sure, and with the dark matter, for instance. But now the progress set of knowledge evaluates both from theory and from observations and from experiments that makes even in some branches of astroparticle physics old-fashioned, because I could call old-fashioned some disciplines and even the name, because I could call cosmo-astrophysics, because you need astroparticle physics, nuclear physics, statistical physics, fundamental physics, gravity, and so on. The point is in the cross correlation on these disciplines, and there is a new era in some sense for astroparticle physics, which I could call cosmo-astrophysics or cosmo-astroparticle physics, if you want, but because it's the evolution itself, but it's not so new. Perhaps it's new for some disciplines of it, but it's more than 40 years ago. I mean,
yes, the
and,
way what I meant is the way everybody knowing about what it is newer than the field, of course. So it's the name, the astroparticle physics, is not common knowledge since so many decades. This is what I meant. For us, of course.
Yes, but
yeah.
yes. But
so
the
so
point
is. So exactly. So what do you think we can? What can we call astroparticle physics? So you say it's an interception, okay, when we put particle physics, cosmology, astrophysics together, we make a mix, and then we get astroparticle physics. But what is the big difference, for example, between astrophysics and astroparticle physics?
Yes, in the fact that you need in astroparticle physics, you need all the physics of particle physics, and you are approaching, it's also the approach in which you are taking into account seriously the fundamental physics, theory, and experiments of particle physics, put together with what is correlated from astrophysics. And in particular, you put that together to solve new problems which have been posed or discovered, which are not understood, which need to be understood, on which are even not completely posed because are much more big questions. The difference with astrophysics is that astrophysics is more phenomenological. And that depends of the approaches. But astrophysics is much more phenomenological without all the fundamental physics and mathematical tools and experiments you need from particle physics and quantum physics and so on. When I talk to some to colleagues, I mean, if you talk about quantum physics, it's in some part of astronomy, it is understood as some exotic physics, because, and that is not the case. But you need is the approach to the way in which the problem is approached, attacked to be solved, which is different from what is usually in astrophysics, and more at all, I should say, from astronomy, which is more empirical.
Yes. So, and Silvia, what do you think?
No, maybe a complementary definition of astroparticle physics. I agree with the Norma said, of course. Maybe it's not even complementary, but a different way to say the same thing is we think, if you know, to rethink the definition in terms of energy scales or length scales. So we can say that we start doing astroparticle physics when we want to describe the microscopic processes which underlie the macroscopic evolution or macroscopic events that we can observe in our universe. So as soon as we increase in energy or we decrease in length, in dimensions, then, as Norma said, we really need the fundamental physics. I mean, quantum mechanics, quantum field theory, string theory, whatever you want. But this because we are really trying to describe microscopic processes, fundamental processes underlying what we see, we experimentally see.
That is absolutely true. I mean, and that depends on, I mean, when of the scale of energy and of the scale of time in the universe, and because of the scales, energy and length, I mean, or size of the object. I should say that, I mean, very, very quickly, that, I mean, to stress the role, the important role of putting together astrophysics, cosmology, and particle physics, fundamental physics, with all this tool, that even the macroscopic events, for instance, cosmic rays, which are essentially process of particle physics, crossing the universe, are crossing the atmosphere too, or the neutrinos, or, I mean, from the different sources, that neutrinos, I mean, or supernova, that is, in this macroscopic object, the way in which you approach the problem, in which really you want to understand from the more fundamental, from the most original, not just satisfied with to present in plots and to make some estimation or numerical simulations, which is other point. Is the approach and the tools you are using too, even for the macroscopic in the universe. So this is another, I mean, with black holes today, I mean, you know, this passed from academic. When I study black holes in my thesis, they were professors that said, but this is academic, very interesting, but this is totally academic. This is, well, it was totally academic. It was not like that. So it's very important to have this perspective in view, that what it appears as not probably today, but well supported by theories and experimental data, could be completely plausible and real if you have enough experiments, enough technology, enough instruments to make the evidence. I think that the example of black hole of gravitational waves, I mean, which are
can
another.
I just try to summarize so that for the students who are listening to us. So when you talk about astronomy, you're talking about observing photons, huh? Looking at the sky, observing photons, observing objects that are coming, and you see, this is mostly when you see what you see. When you move to astrophysics, already you have instruments that are giving you better measurements about these types of processes. And also you're putting together not just what you observe, but an interpretation, phenomenological or interpretation of what you observe, as you were mentioning. When you move to astroparticles, you put together a lot of what we have found here on Earth, namely charged particle physics, and detectors, and what you can observe coming from all directions, and the multi-messenger aspect of this is fundamental. When you get all these signals from the manifestations of different phenomena that you can go back to the lower energy scale that you can. No? Yes. So this is a way that also has to do with the observational capabilities that we've been having and the technological developments that we've been able to make during the last 200 to 400 years, I don't know. So this is just to give a perspective for the students who are listening, so that they have a more concrete...
I agree, Patricia, I agree. I think this is important because it's the way in which we are in the evolution. Yes. And that is why I want to stress precisely that is even if there is inertia in the language, you know, yes. Because when we invent things or discover things with its own words, and there is a inertia from the past language and so on. Mm-hmm. Even that, I want to stress that the difference, I mean, what we call astronomy, astrophysics, astroparticle physics, depends on how much physics do you understand. I think that is very important. Yes. I mean, I think that it's very important. It's very important for students who want to make their career set or have the ambition to be astroparticle physicist or whatever, theorist or astrophysicist or cosmology, whatever. It's very important to have in mind that the important topics, the important disciplines is to know physics. Even if you decide to be astronomer, even if you decide then to construct instruments, because the people who really understand the physics, whatever they will feel, astronomer, astrophysics, or particle physics, whatever, have an approach which allow to go deeper in the how to pose the problem, how to pose the more essential, and how to go deeper. I mean, I have my experience with my school, who have more than 30 years, and which we constructed, I mean, with all the people who constructed. I mean, I am an example, and Héctor de Vega is another example from the most pure theoretical physics, that we wanted to understand the universe with the physics. And then it was the adventure of the construction of the standard model of the universe. At the 90s, we didn't know about what was called a standard model of the universe. What is
the standard model of the universe? But maybe
what is the standard model of the universe? We know what is the standard model of particle physics. Good. And you pose the question about the Higgs and so on. So this appears also a phenomenological model in which you have as a framework for the expansion of the universe general relativity, for the description of relativistic gravity, Einstein's general relativity, the extension to relativist to very high velocities of Newton gravity. That's for the framework of the expansion of the universe. You need field theory, I mean particle physics, or to describe the Big Bang nucleosynthesis, I mean the different percentage of the matter which is composed the universe. And the discovery is that the universe, what was more surprising, and is rather recently said, is essentially filled 4 parts. I mean, more than 70% of the universe is a cosmological vacuum filled by what is the vacuum. We don't know exactly which are the particles which compose this vacuum, but very, very low energy. And is filled by this kind of energy, which is the cosmological vacuum, which at the discovery was called dark energy. And that is the universe today is essentially empty, and that is why is dark energy is majority, 70%. And the other part of the universe, what is matter, is that is composed by kind of matter. I mean, the 80% of the matter is composed by what is called dark matter. That is particles which are not inside the standard model of particle physics, which are beyond. It could be, we will discuss later. And now, as the stars, as the photons, you know, you mentioned, Patricia, and the stars and the planets and ourselves, is a very, very tiny percentage of radiation, of course, and the atoms which we know. That is the universe today. It was not like that at the very early set at the time of grand unification, 10 power 14 or 15 giga electron volt, and there were some little fluctuation from the vacuum, which was also the vacuum, but a very, very excited vacuum, and semi-classical or semi-quantum, in a stage which is called inflation, in cosmic inflation, is the expansion but accelerated. Today, because of the dark energy, we have expansion accelerated by very, very lower than the accelerated expansion was at the very early beginning. This era, which is very short and very consequent, have the fluctuations, and this is what was making in evidence but all the fluctuations of the so-called cosmic microwave background radiation. These backgrounds of photons at 2.7 Kelvin, 7, I mean, with most precision, which was discovered by Penzias and Wilson in 66, and then in 68 more interpreted, and which is the remnant of the photons of the Big Bang. All that are the pivots of the standard model of the universe, which allows to make this puzzle to show the different eras of the evolution of the universe, because from those fluctuations, which has been completed by Planck satellite, the map, COVID satellite in the 90s, and which gave several Nobel Prizes in the disciplines, all these Nobel Prizes, and then this put it together and make this standard model, and even inflation produce primordial gravitational waves, which have not yet detected, and which is expected. But these primordial fluctuations, which are the fluctuations of the matter side, the little first fluctuations of the matter of the vacuum because of general relativity, these have been detected, and because of the microwave background of the anisotropies, because this little fluctuation make that when you see you point in the sky, you don't see the same temperature in the different direction. It's what is called an anisotropy. And this is the discovery of the anisotropy by Kobe, and later the Planck, the European, the WMAP, NASA, and then the Planck, everybody knows the picture, European satellites, then after confirmed. And this this is really the fingers, I said, I mean, the imprints of the beginning, or at least one part of the beginning, from which the galaxies and the large scale, what is called large scale structure, this cluster of galaxies, these groups, and which, I mean, are distributed, the matter in the universe, these are consequences of that. And that can be also checked from other
so we have experimental evidence.
lenses and so.
Yes.
Thank you.
So sorry, I just wanted to give the room also to the other participants, but thank you very much, Norma, for for your comprehensive explanation. And I'm sorry, I had some problem with my sound in the meanwhile. Naoko has been with her hand up for some time, so maybe can also comment on this.
Yeah, so I'm sorry, I'm actually on your side, Patricia. I'm an experimentalist, so let me give you, now I'm also, my background is in particle experiments, so let me give you that sort of perspective. So I'm a neutrino physicist, so, you know, what's very exciting, I think, especially for the next generation of students coming up who will be, you know, prominent scientists in a couple of decades, is that, you know, in the interface of astronomy or astrophysics and particle physics, there's an interesting, you know, very mutually beneficial relationship. So as you know, particle physics, when you go to higher energies, when you go to lower energies, it's nuclear physics. But when you go to higher energies, we keep building these very large accelerators like the LHC that many of you know, this is the thing that can accelerate particles to the highest energies, right? But at some point, the man-made acceleration cannot be enough, right? Like we can only accelerate up to so many PeVs, or like we can only make such big accelerators. So then the sources, especially for me, the sources of these neutrinos come from the heavens, right? From space, because there's these extremely powerful accelerators out there. And that creates neutrinos at energies that we can't create on Earth yet. So there's this very interesting relationship in neutrino astrophysics where, the particle physics can be done using the astronomical sources of neutrinos because they can reach higher energies. And we can learn about particle physics of neutrinos from the sources that the heavens give us, right? And also, and this is my field, what I'm about to say is my field, is the other way around. We also realize that because neutrinos, the particle physics of neutrinos is so interesting and unique that they can inform us about the heavens, about the astronomy, about the astroparticle physics of the world. So it's this both relationship that, particularly in neutrino physics, that we can learn about neutrinos from the neutrino produced in the sky, and we can learn about the sky because of what we know about neutrinos from the Earth. And I think so this is where I work in experimental physics, and that is a very exciting field to be in right now. And I recommend all of you to have a look at that.
So you work in the ice cube experiment, which is a quite interesting experiment. Can you just tell us briefly where it is, how it works, just like a few minutes, so that we can,
yes,
so it's a really...
Yes, so we are at the geographic South Pole. So unlike the magnetic South Pole, the geographic South Pole is where the Earth spins around. So if you have a globe, it's where your spinny stick intersects the Earth. That's where our detector is. And we're not there because it's the South Pole. We're actually there because there's a lot of ice there. When I go to the South Pole and I stand on the ground, I'm actually standing on 3 kilometers of ice. It's a huge glacier ice. And we need that big detector because neutrinos are hard to detect and they're rare. The high energy ones that I'm curious about are rare. So we needed a big block of ice, and that's why we're there. And like many particle detectors, we just use interactions and Cherenkov radiation of produced particles from neutrino interactions to look for neutrino interaction signature. So we have over 5,000 PMTs buried in the ice in a cubic kilometer scale, which is quite large. So I said that like it's nothing, but if you ever want to run 1K, that's huge. So you go 1K this way, 1K this way, and 1K this way. So you can imagine the size of our detector. And yeah, we are a very large international collaboration that uses this for particle physics, for astroparticle physics, for astronomy. So we are at the boundary of many of these fields, and maybe cosmology too one day. So.
And then I have to ask a non-scientific question. Have you ever gone there, actually?
Yes.
Ah.
it was quite a trip. Yes, I've been there. My favorite video, maybe if we have time at the end, I can look for it. My favorite video of myself is running around the world at the pole. So I just run around the pole and say, I ran around the world.
Wow,
but
nice.
I like to show that, yes.
Yeah, thank you very much. That's amazing, Naoki. So Djuna, you had your hand up, so.
Oh yeah, okay, yeah. I lowered it because we started talking about the neutrino experiments, and it was very, very interesting. But I just wanted to sort of, Naoko was talking about like in astroparticle physics, why it's kind of really interesting is one reason is that like the energies involved, right? Like in extreme astrophysical environments are hard to recreate on Earth. Like I think in particle physics, we often think about like energy, but then also interaction strength. So neutrinos are also like examples of very elusive particles. They don't interact a lot with the particles of the standard model, but there's potentially other very elusive particles. Like dark matter could be one of these very elusive particles, for example. And so these are also very hard to create on Earth. So even if you have enough energy, you can have a very light but elusive particle, and you would have a very hard time detecting that on Earth, because it's very hard to create these particles.
Yes, we've been looking for them at the LHC, for example, and we
for example. Yes,
yeah.
exactly. So then there's many experiments on Earth looking for these very elusive particles. But what in astrophysics, you also have access to these very extreme environments like the cores of stars or supernova explosions. And there you have actually, you're not concentrating like some sort of like a beam, the energy into like a very, very small environment. You have actually a whole star where like particles can be created. And so sometimes by just looking for these kind of extreme events in astronomy and kind of monitoring like very closely how that happens, you can potentially detect evidence that there were these very elusive particles which played a role. Supernova explosions are a good example of this, because we know when a supernova happened, like from how the kind of remnant cools, you can learn about like elusive particles like neutrinos being emitted because they carry away energy. And so in this way, we can also probe the existence of, very elusively, like very weakly interacting particles, which you would have a very hard time doing on Earth.
Yes. That's true. So we are mentioning also these dark matter experiments in which you look directly for the evidence of particles crossing, well, in a given halo that the Earth would cross, and then you would see them underground. Like we have some examples, some of these experiments all over the world. Yes,
that's true. Yeah. And if you take your favorite particle and you look at, for example, these plots that are made looking for this particle, you actually see kind of competing ground-based experiments like these kind of dark matter experiments that you mentioned and astrophysical constraints on one plot. I always find it very fascinating how we can measure detect the existence of this particle in so many different ways. And one is by looking at the skies, and one is by building an experiment here on Earth to directly look at the interactions.
Yes, actually, then we are putting everything together, and it's quite interesting, this field, because you get to put all knowledge, like Norma was saying in the beginning, we put all knowledge we have on physics that we can put together of the universe, and then we put everything together and we extract these plots in which we have data from different experiments all over in sky and on Earth. Katy.
Yeah, I guess I just wanted to sort of, since we're talking about exciting things, I guess I wanted to bring in gravitational waves and binary black hole mergers, since that's another sort of exciting development. And I think, all of this sort of question of astroparticle physics, is really comes down to actually observation. So we should, thank the experimental physicists who actually, set all these things up, because, it's really these observations that we're having now that are driving this excitement in the theory community with, what can we actually see? We are really probing these extreme environments. This sort of another really great example of this is the observations of binary black hole mergers. And up until now, that's been very much a kind of astrophysics application where we understand more about the black holes that exist in the universe. But there's also this kind of interesting idea that we could actually use these merging black holes to probe the environments of the black holes to sort of learn about more what's going on around them, or that they could in some way act as kind of detectors of particles. So particularly if there's some, concentration of dark matter around the black holes when they merge, could that give us some interesting signal? So that's another thing that's kind of driving, I think, this interest in, multi-messenger, astroparticle physics. And that's really exciting. I just wanted to bring that up. I'm sure other people probably have things to mention on that too.
Yeah, I think it was Norma and then Naoko, or the other way around. I don't know.
Yes, yes, I am. Precisely, I was thinking when I talked about primordial gravitational waves and the way in which we go from fundamental physics and then to applications and technology, the needed technology. And these gravitational waves, that's why I said the evolution of astroparticle physics or astrophysics from the point of view of fundamental physics, because gravitation also is needed in astroparticle physics because of these macroscopic objects, sources, whatever, merging, or the black holes supermassive at the interior of the galaxies, which are have the accretion disk and very energetic particles. All that is also astroparticle physics, depending on the way you are approaching the problem. And then is a very expanding, very active because of observations on a very old theory, because we do not forget that accretion disk, plasma physics around these black holes, and a supernova explosion, all that, and black holes, even all that were the 70s, the 60s. The black hole name was coined in the 60s, in the late 60s. And that is evolution. So this is a very clear examples on that. Now, a quick point, because it's very interesting for students, I think, about dark matter, which was one of the beginner problems of astroparticle physics, and which is still there, and which have not been detected. We have indirect evidence from the astrophysical observations in galaxies and also in cosmic microwave cosmology, but have not been directly detected and not in the laboratory. And it's a problem. And that is a problem because it's more now than 30 years than dedicated experiments almost around the world were looking for these particles at an energy scale which is not the scale that was thought at the beginning, and then inertia continued, and even today. But that is not the dark matter. That's very heavy dark matter, which were called WIMPs, are weakly interacting. That's true, but not at the very, very high energy scale in which they are looking for. Dark matter is lighter than that, is in the masses of kilo electron volt, and perhaps in the neutrino family is one of the keys for the dark matter. And whatever be the particles, need to be a fermion and need to be a mass in the kilo electron volt and not in the giga electron volt, I mean, powers very, very heavy. LHC was supposed to give, because of supersymmetry, LHC, the program, the primary program was the Higgs, but it was old-fashioned for LHC, not very pushed, but discovered, grid. And the primary was supersymmetry and the wind, the dark matter particle. Supersymmetry was not there because supersymmetry is broken at a very much high energy scale, which is grand unification scale almost, and the particle, the WIMP at that scale is not there. It's not there because
so I have a provocation here. So we don't know what
I said that because it's important for the student.
Yes.
One thing is to do papers, is to be in a group, to have a shop, to go to whatever be woman or man or whatever. One thing is that, which is in any case fascinating, but the other thing is to have the ambition to make discoveries, and that is the difference. In gravitational waves, there are discoveries in those parts because they were constructed at looking at the right energy scale, and that is very important. Thank you.
I have a provocation. So, string theory may explain dark matter because we always talk about WIMPs and supersymmetry, but we haven't measured supersymmetry. We don't know if supersymmetry is real. So this is a provocation. So then I had Naoko, but I would like to pass the floor to Silvia before, if you excuse me, Naoko, because I haven't heard her yet about astroparticle themes. And the provocation was, can string theory tell us something about dark matter that we don't know what it is?
Well, I can answer the provocation with another provocation, which is, string theory can explain everything. But this is not a plus for string theory most of the times. It is a minus, because the fact that it can explain everything, and it can explain everything in many different ways, gives us too much freedom. So we don't know yet. I mean, we are at the stage where, for sure, we have in our hands a very powerful mathematical framework, a very powerful theory, but still we do not know how to use it effectively to describe phenomenology in a very, precise and unique way. We have many.
Yes, what you mean is we need to have a signal that is specific from string theory.
Yes,
so that people can understand what
this would be the best thing to get, of course. And you might say where we can get a signal, because we will never reach experimentally energies where you can detect a string, of course, because string you need to reach 10 to 19 GeV, which is much far away from what we can do we can do in accelerators today. But somehow cosmology, and in particular the standard model, the cosmological standard model, which seems to describe the evolution of our universe in a very good way, I would say, and definitely a good way, basically is providing us with another set of potentially positive experiments in terms of, detecting strings, because we know that if strings exist, they have to be present, they have to be detectable when you reach these kind of energies, which means very tiny dimensions, 10 to minus 35 meters, something like that, which is the Planck scale. And where these dimensions were present, of course, immediately after the Big Bang, because we know that according to the cosmological model for the evolution of the universe, the evolution is expanding from an explosion. And originally the universe was a point. Okay, immediately after the explosion, we really had enough energy and so tiny dimensions that strings, if existed, they were there. But now we know that there is a way to somehow understand or investigate how was the universe immediately after the Big Bang, which is looking at the cosmological background, the cosmic microwave background.
The fluctuations in the CMB.
The fluctuations, in fact.
Yes.
So the hope at this point is that we might be more lucky there in this kind of observation, this kind of, we call it experiments, in finding some, even secondary signal from strings rather than trying to find strings.
So you'd be looking at
scattering processes,
indirect signals.
Yes. In fact, there is a lot of activity which is called goes under the umbrella of string cosmology, where starting from prime principles of strings, you may develop different cosmological models which predict what you should observe. And of course, now I think they are already at a good level where some observations, for instance, from Planck satellite can be used at least to select which are the bad models. This is already something, because you can, clean your table from whatever is for sure is not working, and restrict this very huge set of possibilities that strings provides, of course.
Yeah.
Now let me answer your question seriously. Of course, since string theory contains everything, in particular, it describes all kinds of particles, because in string theory, the fundamental object, this just little explanation for students, the fundamental objects of string theory are strings, so one-dimensional objects which propagate in a space-time and which can fluctuate. We know that a string can fluctuate according to some normal modes. Every single mode is associated with a set of quantum numbers, which can be interpreted as the quantum numbers of a particle. So if you put together closed strings, open strings, you really can produce, using, through the fluctuation of strings, all spectrum of possible particles with all possible masses, all possible spin. So string theory, for instance, predicts the existence of some scalars like the dilaton, the axion, which might be good candidates for dark matter. String theory is consistent only if there is a supersymmetry. So we hope that at a certain point we may detect some even secondary signal of supersymmetry. And supersymmetry means having a lot of other potential possibility for dark matter, all possible SUSY, that's a SUSY partners are there.
In SUSY, we have already restricted a lot the phase space, the parameter space, given what we have been measuring at the colliders.
Mm-hmm.
Yes? Okay,
yes,
so there's also already some restrictions for SUSY. I don't know if Norma wanted to comment on something Silvia was saying. I had also Naoko.
Yeah, I'm sorry, but I worked in string theory, and introduced it for cosmology. When I passed my sabbatical at CERN with Gabriele Veneziano, the group there that were working. And the point of string theory is that they have the revival and all the development till was precisely the discovery of microwave anisotropies, which string theory is not able to reproduce. And even, as Silvia said, they have problems to reproduce the phenomenology in which even the Higgs, you don't have a clear way to obtain from a string theory, which is a problem for a theory which have many merits, but was called theory of everything, and cannot give the Higgs and cannot give the fluctuation of the cosmic microwave. So that make that make some inflection point. But inertia, you see, inertia, is one force which in the communities which I'm working, it's very, very strong. And then you have people that were doing models and continue to try to make the parameters to construct different ways and so on. There is
it's
no
a
hope.
production factory, yes.
Yes, and so I am transmitting my experience for people who are looking, for the young generation, which are looking for subjects which are promising, which can give them discoveries or set new results. And for string theory have not given in string cosmology new results because the way in which it's formulated is seen that people said, have a lot of aqua, have a lot of universe, you can explain everything, but not our universe. String theory have many problems.
Is it true, Silvia? We cannot explain our universe?
No,
I don't think. No, I disagree.
Cannot
I disagree with this
our
statement.
Can explain the unification of forces. Can explain the unification of forces in the right way, including gravity, the graviton, but not inflation, but not the cosmic microwave with the fluctuations.
But it's not incompatible. Is it incompatible? No, it's something different.
The problem is
different, but
let's hear Silvia.
No, what I'm saying is that it's not true that it is impossible to describe microwave fluctuations, or the Higgs, or how to get to the standard model. The problem is that we manage, using string theory, we manage to get, for instance, the standard model, the Higgs particle, whatever you want, not in one single way. Because let me put this statement in a more. No, let me explain. Probably students do not know. The other thing that string theory predicts, which may be a plus according to some people, maybe according to some other people, may be a minus. The string theory lives in more than 4 dimensions. Particular superstring theory lives in 10 dimensions. So in order to get a phenomenological model, which looks like, for instance, the particle standard model, you have to do something to bring the 10-dimensional string down to 4 dimensions. What do you do? Typically, what you do is to think of the 10 dimensions as made by 4 extended dimensions, plus 6 tiny dimensions wrapped around some tiny internal space. The problem is that we do not know anything about this internal space, and we do not have any kind of, let's say, even secondary signal from experiments to decide which is the best choice of internal space and which are the effects of this internal space on what we should observe. So that's the point, is that you have, I would say, infinite ways to get a standard model. This is at the moment, what I would consider the weakness of string theory, but at the moment, because
because in summary, you can formulate it in different ways.
Sorry?
I was just trying to help with the wrap up. So in theory, you can put the bulk, everything in the bulk, in very different ways that we cannot access it, so we don't know experimentally how to access what is there and what are the rules inside the bulk. This is the point.
Yeah, according to which kind of internal 6-dimensional space you choose, you will produce different, effects that cannot be detected.
But it's a very powerful tool. It's a very powerful tool.
The problem is that, the point is that it is a very, string theory, in fact, let me just conclude just saying that the string theory was born at the very beginning, trying to explain, phenomenology, trying to formulate a theory, consistent theory beyond the standard model, because we know that standard model beyond, the TEV, TV, energy may have, and indeed has some problems, but it has been later developed as a very, let's say, very powerful mathematical framework, where now we can pick up even a lot of new ideas. For instance, the idea of a holographic description of gravity is a string production, and I think
this is very interesting, but we don't have time to go into
yeah,
this.
I know.
I've been reading about it lately, and
okay, but just to mention that, you know, strings advanced in the meantime.
Thank you. Yeah. But Naoko, you had your hand up a long time ago. I'm sorry.
No, it's okay. This was interesting. So a while ago, I think Katy said, we want to thank the experimentalists for the observations. And I was thinking, oh no, but we want to thank the theorists for telling us where to look. And I think this is something interesting about astroparticle physics, is that, you know, of course, in every physics, the theory and the experimental community work, you know, in tandem, but this cycle is very close in astroparticle physics. And I think this is what's exciting about it. So in my field, like, we would make an analysis or an observation, and then the theorists would update their models, and their results would then inform us where to look again. And then we would go back with that new knowledge and, you know, try to do a better analysis. So the closeness of the cycle, I think, is what makes astroparticle physics exciting. And I just wanted to say that.
Yes.
It's very exciting.
Yeah.
And
astroparticle physics is very exciting. Gravitational is very exciting. Gravitational physics, set black holes. I mean, all what I have mentioned, and this way in which we are, I mean, going, and then you come back, and then to check, and this it is in all disciplines which are active. I mean, in many, is the way in which science works. In some, yes. You need robust observations, fiable instruments, and also good theory and theorists or phenomenological people to well interpret and go in the direction, to point the instruments or the satellites in the direction in which you can find something. Otherwise, and for that you need the energy scale, you need something before to have, because the surprising is prepared before. Now, I want to make a point also on string theory, or on brains, or, I mean, all this, I mean, higher dimensional, and even modified gravity, which also came, I mean, with some confusion these days. And I want to say that in the universe, I mean, in the very early universe, we test the observations, it appears that when you understand, is not so exotic, the physics is not so complicated. And the point with the string theory, which has its merits by its own, I mean, from mathematics, if you want, that is existence by itself, and which have been applied more these last days to also statistical mechanics, to different integral systems, different topologies, different kinds of branches. Is that for the universe, it's very difficult to implement, and nobody, of course, you can write papers, but to check the observation, to have the right scale of inflation, which inflation is an attractor of the equations in field theory. An attractor is something which is very strong. And with the string theory, you don't have the right scale for that. And so this is a problem. This is a problem for the way in which you can implement with the tools today string theory. So that is why it's very difficult. And of course, you can continue to do same, but it's not, in my view, and for the understanding from the point of view of theory and observations, is not a fertile way for cosmology in its present day formulation. And with holography, well, holography came, but irrespective of string theory, you have holography. So, and that is also a good way. And a good way, holography, and all what came, which is the last Nobel Prize in Physics this year, is the quantum information way in which you can understand physics as even technology. The entanglement, I mean, all these also very, which were thought as John Bell, even Einstein for the Einstein-Podolsky.
Can I just say something here? So the problem here is that something we haven't mentioned. We just mentioned about cosmology, gravitation, and particle physics, but we didn't mention one thing, is that we don't understand together, as we all know, quantum physics and general relativity.
Well, we saw.
And this is the question.
We mentioned because we mentioned unification.
No, but I'm mentioning it in a clear way so that students can understand.
Yes.
And so this is the question. And when we talk, we don't understand. We cannot put together our two models. Well, there are more, but in a way that makes sense today. We don't know. There's a lot we don't know.
Well, you say, I mean, the question was posed more than 50 years ago.
Of course.
I mean,
but you still don't know the answer.
Still, we don't know the answer for dark matter. We still do not know the answer for dark energy, which is.
So the nice thing is for students is that there's a lot we don't know.
I want to add that we need also to make to update the language, because it's not true that we don't know. We don't know nothing as no. The way in which was posed. We know, and there are progresses, and we know directions. And the way, the most difficult way is precisely to make the synthesis or partial synthesis confronting theory and observation, which are the direction needed. And that is socially also a very difficult point, because communities do not want to accept sometimes that there are the models which are discarded. And that is, and you need, because in any way, in any case, the experiments will go on and make that take time, and then things or directions start to be clarified. So for the problem of general relativity and quantum physics, it's a old problem. There are today the ways, there is no, at least, the ways which do not work have been tried. It was legitimate to try it seriously. There are formulations from Dirac even. And then after, things start to be clarified, and then it needed to be made to differentiate the different approach. And with the string theory, it occurs also that give the sense for the one part of the difficulties, but not touching.
Sorry, yes. Norma. Thank you for your contribution. I really have to talk now because we're running out of time and we have some questions from the audience.
So we have questions from the audience. Yes, but I just wanted Silvia as her hand up. Thank you, Norma.
Well, I don't know. Maybe I take more than 1 minute to answer Norma, because I'm used to kind of criticism like Norma is doing to string theory. So let me just tell you that whenever I hear this kind of criticism, I like to mention one example. So in 1954, Young and Mills formulated gauge symmetries and gauge theories to describe fundamental interactions. And, according to this kind of criticism, we can say that they simply, at that time, in 1954, they were just inventing things, fancy things to write papers. And we have to wait until, it was, I think, in 1982, 84, when Rubbia discovered the mediator, W and Z mediator of the weak. So, sometimes you have, if you want to really do fundamental physics, you have to shoot in the dark, because you shoot, and sooner or later you take something which has been you can be proved in the future. So
yes.
Yeah,
Thank you very much.
Bruno?
So I have a question from Bruno.
Yes. Okay, so I have a neutrino question. So we have neutrinos and we have antineutrinos, but they don't have charge. So my question is basically, what's the difference between them?
Well,
I can give you an experimentalist answer.
Okay.
You can get a more in-depth answer from the theorists of the committee, but I think the honest answer is we don't know. We don't know yet. There's a handedness to particles, so that might be something that will distinguish the types of neutrinos. But in fundamental particles, we've never had a neutral particle other than light, obviously, other than photons. So we've never had to ask this question. And I think when neutrinos were massless, it was a little bit simpler to try to formulate answers. But now that we know that neutrinos have mass, but very little mass, so then helicity and chirality are two different things, right? So now I think the honest answer is we don't know. And we do have experiments around the world trying to answer, or at least partially answer that question. And that would be like double beta decay. Neutrinoless double beta decay would be an experiment that contributes to answering this question. So we do have probes, but I think honestly we don't know.
Yeah, so they could be their own antiparticles still.
Okay, thank you.
Thank you very much. I don't know if anybody else wants to comment on the neutrino puzzle. And I don't know if also Djuna and Katy want to say something. We need to close, but no. So if not, okay. Thank you very much for your presence. It was really nice, and it was quite lively now at the end. Huh? And and I will pass the word to Vasco. He organized this. I thank him very much for this. I think it's very important to have this kind of debates and the discussions, and the students are really okay. I thank them for my part, and I pass the floor to Vasco. And very nice to have met you all.
Well, I think this was an amazing event, and I want to thank the members of the panel again for accepting the invitation and making this such like an interesting discussion. I would also like to thank, I didn't organize this on myself, so I would like to thank Bruno Simeão, Carolina Riolin, Miguel Melf, and Madalena Nunes, who also have been involved on the organization of this event. And yeah, it was amazing. Thanks very much. So I think we can, I'll now pass the floor to Madalena. She also wants to say something.
Yeah, I would like to emphasize the words of Vasco and thank you with all my heart to all the researchers from all over the world for your time and for being here. And also thank you so much to everyone who participated in this beautiful roundtable. I'm so delightful. It was amazing.
Thank you very much.
Thanks for having us. Thanks
Thank
for
you all.
Yeah, thanks very much. It was great.
Yeah. So
well, and answering to Norma's question, there will be a recording online on our YouTube channel. I'll send you to a link to email then. Well, thank you.
Thank you. Bye-bye.
Thank you so much.
Bye.
Bye-bye.
Bye-bye.